Atoms and atomic theory. So we are in the book here, and we already know the answer to these questions. But before 1803, we didn't know all these questions, right? Because 1803, right? John Dalton came up with atomic theory, right? So before this, we had four elements: earth, fire, air, water. And so, I mean, people knew there was a difference, like they knew about gold, and we already talked about some of the Latin names, natrium, calcium. You had, they obviously knew water, they knew salt, right? They knew limestone. They knew some of these compounds. They knew all the earths weren't the same. They knew different types of tree. They knew different things, different spices. A lot of things we knew, but we didn't come up with the idea of atoms. All right. Okay. And so, and I believe, if my history is correct, that either Aristotle or Plato, one of those guys, I think it was Aristotle, kind of went against somebody else and came and said there was just the four elements. I think China had 5 elements. All right. But this really didn't change the scientific community until 1803. And atomic theory, and Dalton came up with atomic theory. He said that all matter consists of atoms. So all matter is consisted of atoms. That's what he came up with. Then he said all atoms of an element are identical. He said atoms combine in whole number ratios to form compounds. All right. He said chemical reactions are rearrangements of atoms and atoms are indivisible. All right, so that was his atomic theory. So when we talk about theories and laws in science, little sidebar here. A scientific law predicts behavior. A theory tries to go on to explain how it's happening. What's happening? All right, why is it happening? That type of thing. So laws predict behavior. So if you're, if you throw a ball up in the air, we know what's going to happen. The ball is going to come back down, right, toward the earth, and we know why. Gravity. All right, gravity is going to accelerate the ball at 9.8 meters per second squared down to the earth. Great, we can predict that. How does it work? Well, that's where the theory comes in, right? We got the behavior predictor, right? Scientific law of gravity. We got that, right? And those are sometimes easier to see or predict, not necessarily predict, but to come up with, because the theory, explain why this is working, that sometimes can be harder. All right, that doesn't mean theories are less important per se. Just saying laws are predicting behavior, and they're very good at predicting behavior. All right, and so his atomic theory, and Dalton was trying to explain how atoms work. What are atoms? So here's my atomic theory. All matter consists of atoms. True. We know there's smaller particles, which we'll get to in a minute, but that's true. All atoms of an element are identical. that, of course, is not true. That has been proven to be false. Now, he didn't know, right? He didn't know. And you'll learn in this course, 1800 is basically when our course starts in history. Not much before that. Before 1800, most of history was trying to make lead into gold, right? You had alchemists, and that was their main goal. Let's make lead into gold, and then we can, get more money. That's still going on today. Now we don't have metal, gold-backed money. We have just money because we said so, right? And so, yeah, back then, kings, the government was trying to make lead into gold, and unfortunately, it sounds like most of the time they're pretty good at making gold into lead, not lead into gold. So, right? But we'll learn that all atoms are not identical of an element. And you guys might already know the answer to that. Atoms combine in whole number ratios to form compounds. That is true. Right? Chemical reactions are a rearrangement of atoms. That's also true. And atoms are indivisible. That's where we're false. We can actually take lead and make it gold now. We could do that. It is not cost effective. It is really not cost effective at all. Way more money to make that. So we don't do that. All right. So now let's talk Lavoisier. All right. He came up with the law of conservation of mass. And this was that mass is neither created nor destroyed in reactions. All right, so we can't create nor destroy mass. All right. All right, Dalton also came up with the law of multiple proportions. And this is some elements combine in more than one ratio, but these ratios are whole number ratios, such as N2O, NO, NO2. Right? NO2 minus, NO3 minus. There we go. There's 5 different NO compounds right there. N2O is nitrous oxide or laughing gas. Right? Some of us had that experience where they tell you, all right, count backwards from 10, and you start giggling around 7, and you wake up a few hours later, and it's really not a good time. We've done that. NO2 is smog. It's a brown gas that maybe some places like LA or like Shanghai, China, really bad. All right, and so these are just different compounds. That's the law. They can combine in more than one ratio, but they're always whole number ratios. There's also a law of definite proportions. I don't know. So there's a law of definite proportions. And the law of definite proportion states that any given compound, right, always contains the same elements in the exact exact same proportions by mass. So what do I mean by that? For example, H2O. It's always 11.19% hydrogen and 88.81% oxygen. Right? Water is always H2O. It's never H4O5. It's just H2O. That's the law of definite proportions. All right. So then, as people studied these atoms, right, as history promoted, two guys that you hear talk actually more about in Chem 2 than you do Chem 1, Michael Faraday, and Savante Arrhenius, two big-time chemists. They came up with the formation of ions. This is where, right, the atoms gain either a positive or negative charge. And we'll talk about that. We'll assume what exactly is going on, but we haven't talked about the particles yet. And then, all right, and oh no. All right, the formation of ions. Guy by the name of Thomson, he characterized the electron in a CRT, which is a cathode ray tube. So TVs, believe it or not, used to be pretty big, not flat. All right, and they used cathode ray tubes to, for power, for the light and whatnot. Computer monitors used to be this way. Nowadays we have these little tiny laptops and whatnot. But like my first computer I bought, it was a desktop. I think it was a Dell, to be honest with you, and it was quite large. Right, the desktop was quite large, and then the monitor was even bigger. It was a 19-inch monitor, which was huge. It was enormous. All right, and then the monitor was 19 inches, diagonal. It was a square 4:3 aspect ratio, and it was probably more than 2 feet deep. And you look at some of the old movies, you can see these monitors. They're huge. Now we have these flat screens, and they're really nice. Right, but he uses the actual cathode ray tube to get the electron. All right. Then a guy by the name of Rutherford, which we'll talk about his experiment later on. Rutherford, right? He proposed the nuclear model of the atom, which we kind of still use today. All right, so if you look at, there's 3 particles and Chadwick came up with one, but we've got 3 particles. So we'll talk about the particle, the relative charge, and the mass. All right. So the first thing we're going to talk about is the nuclear model. There's going to be a nucleus. Let's make it circular. There we go. So here's my nucleus. And then we're just going to kind of draw a cloud. Not a circle, but a cloudish. It's cloudish. All right. It's somewhat spherical. So there's 3 particles. There is the electron, which the symbol is going to be E negative, and they are outside of the nucleus. Right? The relative charge is -1, and the mass would be 9.11 times 10 to negative 31 kilograms. Or 9.11 times 10 to the negative 28 grams. The next one discovered was the proton. P plus 1, and that mass is 1.673 times 10 negative 27 kilograms, and that's in the nucleus. And the last one is the neutron. And 0, no charge, 1.675 times 10 to negative 27 kilograms. That's also in the nucleus. Alright, so now, almost the entire volume of the atom is taken up by the electron. So that's almost the entire volume. And almost the entire mass is in the nucleus. Alright, so let's put those in perspective. If you've been to a huge stadium, big football stadium, even a big basketball arena, think of a softball or basketball in the middle of the arena, and that's the nucleus, and the size of the arena is the atom. That's what we're talking about. Alright, so almost all the mass is in this little tiny thing in the middle of the atom. And all the volume is due to the electron going around it. Alright, so that's what's going on with the atom.